All right, hello physics fans. Today we're going to be talking about Lenz's law and inductance. Last time we talked about induction, and just to keep us honest, so far we've got a lot of a lot of right-hand rules that we've talked about. We've talked about magnetic forces. We've talked about how currents cause magnetic fields. We've talked about the dipole model, and we've talked about Ampere's law. Keep in mind that there is a quiz due on Monday, so please work on that over the weekend. Here's a standard type of quasi-quiz question. It says, consider two parallel wires carry current in opposite directions. Which one of the following statements is true concerning this situation? So in this case, I would have that this was the picture that I had in our last video. I had two currents running side by side, and they would pull each other together. Now, in that video, I also said that if we had two currents that are running in opposite directions, they would push each other apart. And the idea behind that, here's our IA and IB running into and out of the page. IA would be running out of the page, IB would be running into the page. And in that case, IB would have a let me put it this way. IA would have a magnetic field that would act on IB. And if you use your right-hand rule where we stick our thumb in the direction of the current A and then have our fingers point, we can find that the magnetic field from current A at the position of current B is pointing up, and then we can use our V, our I cross B gives us F to find the direction of the force. So here would be our force on that. And we could do a similar thing over here and find that both of them are pushing each other apart. So in this case, the two wires will repel each other even if no external magnetic field is applied to the wires. So in this case, the wires themselves are creating the magnetic fields that act on each other. And that causes a Newton's third law type of equal and opposite forces of one wire on the other. Now, I assigned a homework problem on this that I am aware, just because I taught this course last year, that students have a bit of a problem with. So I'd like to spend a little bit of time just looking at it. It says, suppose we've got two long thin wires that carry currents from in the positive z direction. Both of the wires are parallel to the z-axis. The 50 amp wire in the xz plane is 5 meters from the z-axis. The 40 amp wire in the yz plane is 4 meters from the z-axis. What is the magnitude of the magnetic field at the origin? Okay, so I think in this case it's going to be useful for us to look at this picture and realize that when we've looked at these sorts of drawings in the past, they have looked different. Okay, so I think this is sort of a spatial imagination problem in a way. Here's our x-axis, our y-axis, and if you can imagine it with me, the z-axis is coming out of the page. Okay, so in this particular case, if I would redraw this picture in the way that I'm used to seeing it, I would have on the x-axis at 5 meters, that's where I would have this current coming out of the page, so that would be 50 amps. And then here at 4 meters along the y-axis, okay, so this would be 4 meters, and then this would be 40 amps. Well, we know the magnetic field from a long straight wire, and we know how to apply the right-hand rule. So if I use this, I should be able to figure out, let's call this, current 1 and current 2. I can find out what the direction of each one of those magnetic field contributions is going to be using my right-hand rule. And then I can also figure out what the magnitude of that field is. So use your thumb, point it out of the page in the direction of the 50 amp, and then you can use your fingers to figure out what the side of your hand is pointing in the direction R from the current to the point of interest at the origin, and then your fingers curling around here perpendicular to the flat of your hand here are going to be pointing in the direction of the magnetic field. Okay, so this is our point of interest where we want to find the magnetic field. The magnetic field component from that wire 1 is pointing in the y direction. Why did I draw this so weird? Oh my god. I've really messed this up. Okay. I don't think I have time to redo this whole video. So, I'm scratch that. And if I had an editor, if I had more competence, this would not happen. But it is happening. This is the world we live in, not the world we would like. So in the world we live in, I messed up the directions. So let's do it again. Here's X, there's Y. Okay. And then looking down on it, we would have here at 5 meters, we've got a 50 amp current coming out of the page. At 4 meters, we have our 40 amps. And let's try it again. So with our X, we can again, let's, confusingly, I'll just label these 1 and 2 again. And for our Y, our 1, we would have our magnetic field pointing in this direction. So there's our B1. And then for our 2, use your thumb, use your fingers, your claws, I guess, we're close to Halloween. Use your B2. Okay, so something interesting two things that we can observe here. In our B1, we can easily plug in the numbers here, okay, because mu naught is going to be 4 pi times 10 to the minus 7th Tesla meters per amp. And then I, they give us as 40 amps. And then our distance here would be 4 meters. So we'd have 2 pi times 4 meters. Okay, so you can actually get a number out of this fairly easily. The 4 and the 40 can be simplified. 4 pi, 2 pi, this would just be 2. So this would be just 20 times 10 to the minus 7th, or 2 times 10 to the minus 6 Tesla. Okay, and you can easily go ahead and find out what B2 is as well. So that's the magnitude of this arrow. Now, I want to point out that in this question they're asking you for the size of that vector, but these are perpendicular, so it's going to be easy to find in that we can just use our Pythagorean theorem. So the magnitude of that total B net, we might even call it, the magnitude of that total B field at that point would just be the square root of B1 squared plus B2 squared. Now, today we're going to talk about Lenz's law and inductance. But last time we talked about Faraday's law and induction. Okay, so it's the two terms are super similar and they mean almost the same thing too, which is a little confusing. here's the experiment that we want to formalize. You've got a magnet, and as you push that magnet into a coil of wire, it causes a current. So you see I've got a very old style ammeter here, and it doesn't even give us currents in both directions. But as I push this magnet in, if I'm not moving the magnet relative to the coil, I don't get any current. But as soon as I move it, I'm changing the flux through through the loop, and it causes a current. So that's what Faraday's law told us. It told us that as long as we have a changing magnetic flux through a surface, we could get a magnetic field. Okay, so we called this Faraday's law. We defined the magnetic flux as the surface integral over the dot product of the B field and the area. And because this has units of Teslas times meters squared, I have to admit, in this part of electrical theory, the units get very snarly. So like Teslas times meters squared. Of course, you could go and keep, a Tesla is the same as, a Newton over meters per second times coulombs. And this would be meters squared. So, I mean, a Weber, you could, and then Newtons would be, kilograms times meters per second squared times meters squared over, coulombs times meters. So I'm just saying I can, if I want, mess around with this and get some slightly simpler units on these things, but I'm not sure it really helps. So that's why they're asking us to think about, okay, so I have kilograms times, not kilograms squared, kilograms times meters squared over coulombs times seconds. Okay, did that help? I'm not sure it did. So this is a Weber, but who cares? It's something that if we put everything else in good units is going to help us to find volts. Okay, so the change in Webers per second, if I take a Weber over a second, that would give Webers per second is kilograms meters squared per coulomb per second squared. But kilogram meters squared per second squared over coulombs is just joules per coulomb, which is volt. Okay, so all the units work out. All the units work out, but it really is a little hard to keep track of things. So just to say it again, the whole point of Faraday's law is that if you have a change in that magnetic flux, it can cause a current. What are currents caused by? Currents are caused by voltages because of Ohm's law, V equals IR. So in our last video, we went through some examples of that. Today, I would like us to review one aspect of this that I sort of didn't talk a lot about. We talked about the fact that you'd get a voltage, but I'd like us to think about what direction that voltage is going to point. Okay? Now, Lenz's law tells us is not really independent from Faraday's law. In fact, it's this minus sign. Okay? And what it's telling us is that the direction of the flux created by the voltage is going to be opposite of the direction of the flux that's being applied to the loop. Okay, so any currents that are induced will oppose changes to the magnetic flux in a sort of magnetic inertia. And here's a picture that's sort of an example of this. The magnetic field from this bar magnet is pointing down in this picture. So as the hand moves that bar magnet towards the loop, the magnetic field in that loop gets bigger in this direction. So the flux increases in the down direction. So the induced flux the induced magnetic field from the loop is going to be pointing in the opposite direction. Okay, and that is what Lenz's law is all about. It's the minus sign in Faraday's law. So let's think about a situation here. It says, consider the situation below. A triangular aluminum loop is slowly moving to the right. Eventually, it will enter and pass through the uniform magnetic field region represented by the tails of the arrows directed away from you. Okay, so this is a B field. Initially, there is no current in the loop. When the loop is entering the magnetic field, what will the direction of any induced current present in the loop? Okay, so this is an application of Faraday's law, and we are now focusing on this minus, which we call Lenz's law. So think about it. As this triangle is moving into the loop, the direction of B, the change in B, is going to be into the page. So the direction of the induced magnetic field from the current is going to be out of the page. Okay? So in this case, the induced magnetic field is going to be pointing like this, opposite the direction of the change in the magnetic flux through this loop. Okay, and then I can go ahead and use my right hand rule and my loop to figure out what direction the current is going around here. So the induced field from this loop as it enters is going to be going out of the page. And so to get that, if I loop around, the current has to be going counterclockwise. A little tricky to think about. Let's try another one. Okay, so it says again, we have a triangular aluminum loop slowly moving to the right. Eventually, it will enter and pass through the uniform magnetic field representing the tails of the arrows directed away from you. Initially, there's no current in the loop. Okay, so that's an important issue to realize. So you get a current. The current is initially going to be going, when it's entering here, we establish that the current is going to be going counterclockwise so as to produce an induced magnetic field that's opposing this. Now, when I am when my triangle is totally inside that magnetic field, it's a constant magnetic field, the magnetic flux then will not be changing. So here's my I as I'm entering. Here my I would just be 0. As I'm exiting though, okay, the magnetic flux is smaller because the magnetic flux has the same value over here, but it's 0 on the edge of the triangle. So because the magnetic flux is smaller, the magnetic flux is pointing this way, but its change is going to be going the other way. It's the same as the sort of idea where your acceleration is negative if you're going forward and slowing down. So in this case, my Lenz's law always tries to act to keep things the same. So in this case, it wanted that. I'm using a little bit of teleological language. It wanted. Okay, this is the same sense in which a thermostat has desires. It's not maybe exactly like the way you and I have desires, but I guess philosophers will argue over that. But in this case, the magnetic field, the Lenz's law will try to keep the magnetic field through this as similar to what it was as possible. So, in fact, the induced magnetic field is going to be pointing into the page in this case to try to keep it like it was. Okay, this idea here is that Faraday's law is always opposing change. It's sort of a magnetic inertia. So in this case, if my induced magnetic field now is into the page, I can use my curl around my thumb to figure out that I would get a clockwise motion around the loop. Let's try one more. Let's say that we have a rigid current, circular metal loop begins at rest in a uniform magnetic field directed away from you as shown. The loop is then pulled through the field to the right but does not exit the field. What is the direction of any induced current in the loop? So in this case, no current is induced. Why not? Well, the reason why not is that this field is constant, and so the flux, remember the flux is just the integral of B dot dA. So it's going to, in this case, be pointing into the board, and that surface integral is not changing over this surface inside the ring because the magnetic field is constant. Okay, so because the flux is not changing, there's no change in it in time. No voltage is induced. Now, in our last video, I did this problem. The thing I want to focus on, so if you want to see me do this part of the problem, I encourage you to look at the end of our last video. But let's think again about the question of, is the direction of the current through R to the right or to the left? Okay, so in this problem, I have a magnetic flux that is pointing out of the page. Okay, so my flux is pointing out of the page, it's getting bigger, and so in this case my induced voltage will, by Lenz's law, try to oppose that direction. Okay, so the induced will be going into the board because the applied is coming out of the board. Okay, so because of that, I can put my thumb in that direction and try to figure out what direction is my current flowing. So it's going like this, and I have to be consistent here, and there it is. So it asks, is the direction of the current through R to the right or to the left? In this case, it would be to the left. Okay, here's another one where we're practicing with Faraday's law. I just want to comment on what direction we would expect the current to flow. In the last video, I already went through all the other elements of this problem. In this one, we've got a flux that's coming out of the board. It's getting bigger because the surface itself is getting bigger as this bar gets dragged over, and so the induced magnetic field has to be pointing into the board. So if I try to put my thumb in that direction and curl my fingers around to see what direction the current must be going, the current must be going like this. So this is the direction of our induced voltage. Now, our last idea for this unit is the idea of the self-induced flux and induction. I suppose I really should put here inductance. The idea of inductance is that it's a quality of the object in the same way that we already have talked about capacitance and resistance. And what it is the ratio of the magnetic flux through an object divided by the amount of current that is passed through it. So for instance, when I put a current through an object like a solenoid, I would go ahead and get a magnetic field inside of this thing. And the magnetic field is not necessarily from an external source like a bar magnet. It's being caused by the object itself. And so the inductance is helping us to quantify how much the magnetic flux responds to how much current I put through that object. Now, it's going to become apparent in just a second why this is important. So, as we said, because a current has its own magnetic field, it will follow Faraday's law, Lenz's law. Okay, that makes sense because those are, laws of electrodynamics. Now, we're going to have some weird units on this. It's going to be flux per current. Okay, so Webers per amp. Of course, you can simplify that if you want. But the unit on it is a Henry. A Henry is a Weber per amp. If you want to, really mess around with that, you can get it to units of something like kilograms times meters squared over coulombs squared. But I would not recommend it. It's not that enlightening. But this gives us a sense of something about the object's magnetic inertia, okay? And we're going to use this more next week to talk about different circuits. But for now, let's just try to see if we can calculate this for instance, a solenoid. Okay? So here's how we're defining the inductance. L equals N times the magnetic flux over I. But this is N over I times basically the area. Magnetic flux is area times the magnetic field. The magnetic field in through a solenoid, as we found using Ampere's law, for instance, is U mu naught, a constant, times I, the current running around those loops, times little n, which is the number of loops per unit length. All right. Now, you'll notice that the current cancels out. So if I'm looking at this for a solenoid, we like to express things in a solenoid in terms of current loops per unit length. And so let's divide both sides of this by the length. So N over L. We're going to divide all of these by L. And what you find then is that L over the length, the inductance per unit length of a solenoid, this is little n, N over L. This is little n, N over L. And so what I get is mu naught times N over L times N over L is little n squared times the cross-sectional surface area. Okay, so just to make sure that we understand this expression, let's say we have two solenoids A and B have the same length and cross-sectional surface area. So the length of A is equal to the length of B. The area, cross-sectional surface area of A is equal to the cross-sectional surface area of B. The solenoid B has 3 times the number of turns per unit length. So N A and NB are related, that solenoid B has 3 times the turns per unit length of NA. Okay, and I should be using little n for that. 3NA equals NB. What is the ratio of the self-inductance of solenoid B to that of solenoid A? Well, in this case, our LB A would be length of A times mu naught times turns per unit length of A squared times the area. LB would be length of B times mu naught times NB squared times area, sorry, this was area of A and this would be area of B. Now we want to find the ratio of the self-inductance of solenoid B to that of solenoid A. So let's put everything here in terms of the inductance of the parameters of solenoid A. So this LB would equal, LB is just LA, so this would be LA. Mu naught is a constant of nature. NB is 3 times NA, so I'm going to put in 3 times little na squared, and then AB is just the same as the area of A. So my LB is going to be, all of these are going to be the same except 3 squared. So it's going to be 9 times LA. Okay, so what is the ratio of LB over LA? It should be 9. Now the reason this is all going to be important is because this effectively acts as a sort of magnetic inertia. Now let me show you what that means. The expression that we're going to look at is that the induced voltage is related to the change in the current. So if I have a current that's changing, I will experience an induced voltage that will cause that current not to change as fast. Okay, so where we're going with this is that we're going to use this type of induced voltage in Kirchhoff's laws to get us circuits that are not as abrupt. So when you use an inductor, often the purpose of it is to cause things not to turn off abruptly or on abruptly, but to have a little bit more of a gentle on and off turn, so you don't damage circuit components. So let's just look at this. Faraday's law tells us that through a component, the induced voltage is equal to minus d dt of the flux. Now, I can rewrite that flux in terms of the current and the inductance. Okay, let me just take this expression right here and rewrite it such that the flux through a component is equal to I times L divided by N. Okay? And I should have an extra N in this law. Okay? For if I have N different loops. So this is I realized I tried to add that and I must not have saved it. Okay, so in this case I would have N times my flux written in terms of my inductance. So I'm going to put this in here as I times L over N. Now the n's cancel out. L is just a quantity that's a quality of the object, so it shouldn't be changing in time. And so if I take the time derivative of this, I should get that the induced voltage is equal to minus L di dt. Okay, so I don't think we have quite enough time to do it in this video, but where we're going with this is the idea of an RL circuit. And the idea is that once your current has been running for a while, this inductor will look just like a wire. At that point, it will have stored some magnetic energy, but it will not impede the flow. But when you turn it on, it will take some time to get up to the final the final current. When you turn it off, when I take my voltage source away and allow the current to flow through here, what's going to happen is that it's going to also take a bit of time for that current to stop. The inductor will want to continue the current going in the direction that it was going. As I said, it's sort of like magnetic inertia for a current. So the behavior of the battery is going to be determined by a time constant, just like we had for the RC circuit. This is going to be an LR circuit. So it's going to be the inductance divided by the resistance. And so it takes some time for the current to turn on. And as we'll find out on Monday, it will also take some time for the current to turn off. Now, I don't want to go any farther today. On our next video, we will talk about the RL circuit, and we'll talk about the energy stored in an inductor. I'll do a little plug for another video on that I've done. This last summer, I was getting a little interested in history of physics, and I thought I would tell you about this video since Halloween is almost here. So there's a video on my YouTube channel called Physics in the Paranormal, and I am a little bit agnostic about these subjects. I don't really know what the true answer is, but it's an interesting avenue of history that there have been physicists who have been interested in spooky stuff. So if you are interested in that at all, I encourage you to go check it out, and it might be good for Halloween. Okay, so what are our ideas of today? Changes of magnetic fluxes and through a loop cause electric voltages and electric currents. The direction of that electric current, that the electric, I should say, voltage, well, current in response to that that induced voltage will act to minimize the change in electric flux. And then finally, current loops called inductors can be used to slow changes in an electric circuit. Okay, so thank you for watching, and happy Halloween.